Infinite limits. What happens as x goes to infinity of x squared? Does it make sense that if x was really, really big and you squared a really, really big number, that would be a really, really big number? And so what we're going to write for this is we're going to say this, as this goes to positive infinity, this keeps on getting bigger and bigger. So we're going to say it approaches infinity as well. I think in your textbook, they will sometimes, when a limit goes to infinity, the answer key will say does not exist, because technically that isn't an actual number that you approach. But what we're going to do to be more specific is we're going to tell if something goes to positive infinity or negative infinity. And there's going to be a worksheet that I'm going to give you next week that has all of those things written out this way. So x squared gets really, really big as well. What happens to this graph as x gets really, really big? It approaches negative infinity. Because you can think of, well, the 5's not really going to matter. We're really looking at negative 3 times a big number. And a negative number times a positive number will be negative. So this limit will go to negative infinity. So if we look at the graph of negative 3x minus 5, it have a y-intercept at negative 5. And it would have a slope of negative 3, meaning that you would go down 3 over 1. And it would look like this. And so what this question is saying with the limit as x goes to infinity, as your x values go that way, bigger and bigger and bigger, what's happening to your y values? Well, they just keep going down further and further and further. And so we would say that as this gets really, really big, your y values are going to get to become really, really big negative numbers. So we write it as negative infinity. Well, yeah, the definition of the limit is something that something gets closer and closer and closer to. So what we're saying here is it doesn't get closer to a specific value, that it just keeps getting to be larger and larger and larger negative numbers. And again, that's why your textbook will sometimes say the limit does not exist, because it's not actually approaching a number. But you'll see some textbooks and some places they'll write that answer as negative infinity because it is still telling us something. It's telling us that as the x values get really, really big, your y values become really, really big negative numbers. So sometimes what you're deciding with limits to infinity is my number getting really, really big or not? And if it is getting really, really big, is it going to be positive or is it going to be negative? So in this one, when you plug in a huge number, can you see that this one's going to be large? Is it going to be positive or is it going to be negative? Negative. So this one would go to negative infinity as well. So we've got a sort of rule here that if your power is bigger than 1 and your value of x goes to infinity, then this will always go to infinity. So if you had an x cubed or an x to the 5 or even an x to the 1.5, it'll just keep getting larger and larger and larger. Here's our next idea. What happens if we divide by a very, very big number? You get a very, very small number. Like if I had 1 over 10,000, that's not very big. And if I went even larger, it gets smaller and smaller and smaller. And so this limit's going to equal 0. Again, graphically, if we think about the graph of y equals 1 over x, that would have an asymptote here and an asymptote here. And your graph looks like that. What we're asking is, as x gets really, really big, what happens to your y values? And you can see from your graph is getting really, really close to that asymptote at y equals 0. So anytime we divide by a really large number, it's going to get closer to 0. Here we're getting to a very, very big negative number. If you divide by a very, very big negative number, it's going to get close to 0 as well, right? And so this limit's going to be 5 minus something close to 0. I mean, if you wanted to show it like this, you could do that as well. I know that 1 over n cubed is going to get really, really close to 0. And so if I subtract 0 from 5, my limit's going to be 5. Here's a little typo that you can fix on there. The little highlighted part, I think yours says n instead of x. So again, in general, if your r value is bigger than 0 and you have 1 over and x gets bigger and bigger and bigger, that limit's going to go to 0. So now when we have an equation with variables in the top and the bottom, what we can do as a strategy is we can factor out the highest power in the whole thing out of the top and the highest power out of the bottom. So in this one, can you see that the highest power that we have is an n? So we could rewrite this, factor out an n out of the top, and factor out an n out of the bottom. Well, the bottom is just an n. What would I get if I took an n out of 2n plus 3? Well, taking the n out of the 2n, you're just going to get 2. How do you take an n out of 3? Be n to the minus 1, or you could write that as 3 over n. Does that make sense? If I multiplied this through, that I would get this that I began with. If you factor out that highest power, well, now these n's will simplify, and our limit is just the limit as n goes to infinity of 2 plus 3 over n. So what we've done is we manipulated our question so that we could write it in a way that we can evaluate the limit. Because we know that 3 divided by n, as n gets really, really big, that's going to go to 0, and our limit's just going to equal 2. So one of the things that I like to do sort of as a shortcut for these ones is I look for my highest power of n. In this case, it's just n. And I look on the top, I have 2n. I look on the bottom, I have n. What's 2n divided by n? 2. And that's your limit. So if you can find that highest power, you can just look at that and ignore everything else. But that would be a shortcut for these ones. So we'll do a couple of these using the method, and then we'll look at the shortcut. So for this one, what's the highest power in the whole thing? N cubed. So if we factor that out, this will become 1 over n. And on the bottom we'll have 8 plus 1 over n cubed. And now your n cubes would simplify. And if you apply this limit, well, 1 over n and 1 over n cubed, those will both be 0. So you're going to get 0 minus 3 over 8 plus 0, which is equal to negative 3 over 8. Again, looking at the shortcut, if the highest power is n cubed, we have negative 3n cubes on the top. We have 8n cubes on the bottom. If you ignore everything else and simplify that, you'd get negative 3 over 8. So I'm going to just give you a couple more where I want you to do the shortcut. Okay? What's your limit going to be? 5. What's the highest power? X to the 6th. So if you look just at those ones, ignored everything else and simplified it, it's going to be 5. We did something like this before when we were graphing, right? You had to graph in grade 12 you had to graph something like that. And in this graph, you found out that there was a horizontal asymptote at y equals 2/3, right? And what that was doing is you were just saying, well, I'm going to ignore everything else and just look at those. And as x gets really, really big, that means that your y value is going to get really close to 2/3. And in your graph had something like this, right? Because it also had at your non-permissible value, you had another asymptote. So we had this idea already last year, but now we're extending it to bigger numbers. What if I gave you the limit, x goes to infinity, 5x to the 7 plus x squared plus 3x to the 5 plus 2 over x to the 6 minus 4x to the 4 plus x squared. What would that limit be? That limit would be infinity. What's the highest power? X to the 7. If you just ignored everything else, you have an x to the 7 on the top of your fraction, which means it just keeps getting bigger and bigger and bigger. What would happen, this same question, but I made this here, x to the 21. Now it's going to be 0, because my largest value is there on the bottom, and now I'd be dividing by a very, very big number. So if you have a highest power on the top of your fraction, well, then it'll just keep getting bigger and bigger and bigger. And if you have the highest power in your denominator of your fraction, well, then you're just going to get a bigger and bigger and bigger number on the bottom, and then that limit will go to 0. Oh, I'll get back to the examples that we have. Find the limit if it exists. What happens to negative 1 to the n? Can you see that when n is an even power, you're going to get positive 1. But when n is an odd number, you're going to get negative 1. And this is going to flip-flop between positive 1 and negative 1 as n gets bigger and bigger and bigger. And because it's doing that flip-flop, is it approaching just one value? No. So for this limit, we would say that this one does not exist because of that, because it keeps flip-flopping back and forth. Which comes to an interesting are you familiar with sigma notation? Have you seen that before? If I write n equals 1 to infinity of negative 1 to the n, sigma notation says add things up. Start when n is 1, plug in 1, and you get negative 1. Then go to n is 2, plug in 2, and you'd get positive 1, add those together. So can you see that you would get negative 1 plus 1, minus 1 plus 1, minus 1 plus 1, so on forever. What is this equal to? 0? Because if you group these two together and then these two together, and you did that forever, wouldn't those always be zeros? And it goes on forever, so you could just do 0 plus 0 plus 0 plus 0 plus 0 plus 0. So some would argue and say, this is equal to 0. And then someone else came along and said, well, I was looking at this, and I put my brackets this way. I put my brackets here and here and here forever. Then what do I get? Minus 1 plus 0 plus 0 plus 0 plus 0 plus 0. So I think this is equal to minus 1. And this is another example. This sum does not exist. Because if you argued it one way, you could say it ends with 0. If you argue it the other way, you could say it ends with minus 1, and it flip-flops between those two. So anytime in math where things have two possible answers that both make logical sense, mathematicians just sort of go, okay, it doesn't exist. That makes it easy. We have a problem here. Someone could argue one thing, and you could say that makes sense. And someone could argue something else, and you could say that makes sense. And then you've got a problem. Here, I'll give you another one. What is this equal to? 0 to the 0. Well, I kind of led you into it that it doesn't exist. Why doesn't it exist? What could you argue that equals? What do you think that should equal? You could argue that it equals 1, right? Because what's 5 to the 0? 1. 4 to the 0? 1. 3 to the 0? 1. 2 to the 0. So you've almost learned anything to the 0 is 1. Okay? So there's one argument that that should be 1. Can you give me another argument that this should be something else? Should be 0. Why? Well, you're like, what's 0 squared? 0. 0 to the 1. 0. 0 cubed. 0. 0 to the 5. 0. 0 to the 420. 0. You have all of those things that could be zeros all the time. So this could have an argument that it should be 1, or it could have an argument that it should be 0. And so this does not exist. So in mathematics, when we have these things that you could argue one way or another way, they just decide, let's make it not exist, and then everybody's happy. Instead of solving the problem? What's that?
Because technically it's like what 0 is equal to infinity to the power of -1, right? So then it would be
0 is equal to infinity to the minus 1. Well, that's not, you can't really say infinity to the minus 1. Like, basically you're wanting to say that 0 is equal to the limit as n goes to infinity of 1 over n. That's okay. But actually writing infinity to the negative 1 doesn't make sense. It's very hard to find that infinity button on your calculator too. You have an infinity button on your calculator? Oh, nice. Well, I mean, if you're using infinity to represent a large number, right? And if you said a large number cubed, that would still be a large number. Now, we don't ever write infinity cubed, but we can say what's the limit as n goes to infinity of n cubed is basically the same idea. What happens when I have a large number cubed? It's going to be large. And so we'll say that that's infinity. Okay. Find the limit if it exists. So you start with a big number. What's 1/2 to a big number? A small number. Does this make sense that this is going to get smaller and smaller and smaller? Do you remember when we started class and talked about limits, I started 16 blocks away from the wall? And then I walked half the distance, and then half the distance again, and then half the distance again. And we wrote out that the sum to infinity was the fact that I walked 8 the first time over 1 minus a half because it made a geometric sequence. And you have this formula that you learned in grade 11 that was term 1 over 1 minus r for an infinite sequence. Now for adding up, so if I wanted to add 8 plus 4 plus 2 plus 1 plus a half, on and on and on, if I wanted to add up the first 100 of those terms, well, then I would need to use my formula for a geometric sequence, which was t to the 1 over 1 minus r to the n over 1 minus r. You don't remember that formula, but you learned it in grade 11. It was on your grade 11 formula sheet. How are these formulas related? Well, if r was less than 1, or actually if r was between negative 1 and 1, and you took the limit and made n go to infinity of Sn, which is equal to the limit as n goes to infinity of term 1, 1 minus r to the n over 1 minus r, look what happens. If r is a small number, like a half, what happened to a half as n gets really, really big? It goes to 0. So this formula that we have is because this part right here, as n gets really, really big, went to 0. And then our complicated looking formula that we learned in grade 11 with 1 minus r to the n over 1 minus r just became this very simple formula, term 1 over 1 minus r. But you didn't have limits back in grade 11, so you just got this formula. Sum to infinity is this. But now you can see where that comes from. Because this part of the formula, as n gets really, really big, just goes to 0. And then that simplifies your formula to just be term 1 over 1 minus r. So we can say either by saying if r is between -1 and 1, and sometimes it's written this way, where the absolute value of r is less than 1. That is the same way as saying that r is between -1 and 1. And also there's a typo in your notes here. I think you need to change whatever letters here and highlighted should be an r. No, it shouldn't be an r. It should be an n. Yeah, it's an x, and it should be an n. Oh, look at that. Perfect recovery. Whew. And then we got one last question. This is a good one for discussion. It's not a good one for discussion. I don't want to talk about it. X goes to 0. What does 1 over x go to? Good. So gut feeling for a lot of people is to say infinity. Because you divide by something very, very small, right? What will it look like? You'll get a lot of stuff, right? If you decide to cut a whole cake into very, very small pieces, how many pieces will you get? You will get a lot of them. So at first, the idea is, oh, the limit as x goes to 0 should be positive infinity. But if you think about it a little bit further, if we do the right-hand limit, remember our right and left-hand limits? If we look at it from the right-hand side, sure enough, if you put a very, very small positive number in there, this will go to infinity. But what will happen if we go from the left side limit? It'll be negative infinity. And what did we learn? If the left-hand limit and the right-hand limit are not the same, then the actual limit does not exist. If you think about your graph of 1 over x, you would have an asymptote here, and an asymptote here. Our graph on this side looks like this. Our graph on this side looks like this. Your right-hand limit means you're getting closer to 0 from the right side. And you can see that from the right side it goes up forever. So then that limit would be positive infinity. As you're coming to 0 from your left side, it goes down forever. So your left-hand limit is negative infinity. Since both of those aren't the same, we would say at x equals 0, the limit does not exist.